say about Cynthia, because again, is that she was actually a colleague of Joe at IBM, so we'll have that perspective as well. Cynthia, the floor is yours.
Thank you. Thank you for inviting me. And that was a fabulous talk and a tough act to follow, but that's kind of what I would expect at a celebration for Joe. So I'm going to talk about measuring our chances or risk prediction in this world and its betters. I think of risk prediction as giving us a defining problem for artificial intelligence. So what I mean by this is risk predictors or scoring functions assign numbers between 0 and 1 individual instances. For example, what is the probability that it will rain tomorrow? What is the probability that individual X will repay the loan? What's the probability that this tumor will metastasize under a given course of treatment? Or what's the probability that individual Y will commit a violent crime in the next 2 years? The problem with all of this is that it's not clear what is the meaning of the probability of a non-repeatable event. This is a deep problem in the philosophy of probability, and it's not resolved. So, for example, we can't just give somebody a loan and see whether they repay it, and then rewind history and give them the loan again and see whether they repay it, and build up some sort of frequentist notion of a probability of this person repaying a particular loan. So we don't have a probability of an event. If we don't have a really good understanding of what is the probability of a non-repeatable event, we don't know what the ideal risk predictor should satisfy. What is the goal of the predictor, of the ideal predictor, and how do we evaluate an algorithm, a prediction algorithm? So you can imagine two possible worlds, for example. In the first world, I'm going to call it the green gold world. It's the world on the left here. All of the probabilities are either 0 or 1. So there's no uncertainty. The only uncertainty that we have comes from maybe lack of access to the information we need to determine whether the truth is 0 or 1. Or perhaps we don't have the computational capacity to take the information we have and figure out whether the truth is 0 or the truth is 1. In a different world, the red world, everybody has probability a half, and uncertainty is completely inherent. There is no predetermined answer. There really is uncertainty. And there's no way to tell these worlds apart. In part, this is because all the observations that we actually have in the real world, whether it's the green gold world or the red world, are of actual outcomes. We have a person, we know whether they repaid the loan or not, but that's it. So everything we have looks like a green gold world, even if the truth is red. And as a consequence, when we try to build a predictor from training data, the distribution on predictors that we will build from our training data will be independent of whether real life is arbitrary. That is, we can have probabilities that are strictly between 0 and 1, or real life is Boolean. And so given that we can't, this unresolvability, we can't ask that the predictor F be correct on outcomes, because there might truly be uncertainty. And F that always says 0.5 is the most accurate description of reality in the red world. So again, how would we evaluate a predictor F? Now, there's a long history of evaluating predictors or forecasters in the online world. So this is not a distributional setting. Nature can be malicious and arbitrary and so on. But think about weather prediction. On every day, the forecaster says whether it gives a probability of whether of rain for the next day, and you want to evaluate this string of predictions. And an extensive literature that sort of begins with Philip David's work in 1982 examines calibration and variations on calibration. So calibration is often viewed as a sine qua non of a forecaster. And calibration just says, say, if we look at all of the days on which the forecaster predicts a 70% chance of rain, then in fact, on 70% of those days, it rains. And this is true for all values of 70. That's sort of in the online world. We're interested in looking at the batch setting. In the batch setting, we have a bunch of training data and we want to, drawn from a distribution, and we want to build a predictor that in some sense that we haven't defined is good for unseen instances. So to describe this more, we have to introduce a little bit of notation. We have individuals I, and we have PI star being the so-called real life probability that individual I will receive a positive outcome, say will repay the loan, for example. And PI star might be integer, it might be either 0 or 1, but it also might be something in between. And we assume that the real life outcome OI star is drawn from a Bernoulli distribution with probability PI star of coming up heads. Let me just pull out a pointer here. So coming up positive. Now we want to build a function f, and it's going to give a model of the world, and f sub I will be the modeled probability that I receives a positive outcome. And then we can look at outcomes drawn from the Bernoulli distribution with parameter fi, which is the modeled outcome, which is drawn according to the predictor f. So the stuff in blue with the stars, that's the so-called real life situation, and the stuff in red without stars is the model world. Okay. So outcome indistinguishability is a notion that has been very useful here. So imagine that we have a collection of distinguishers. These are just algorithms or circuits. And distinguishers are going to try to determine whether an outcome OI is drawn from real life or is instead drawn according to the model of the world given by F. So here we have our putative distinguisher, our algorithm A. It's given as input the individual I, the modeled probability Fi, the modeled prediction Fi, and an outcome OI. And the algorithm is trying to guess whether OI is the real life outcome, in which case it would be OI star, or OI is a modeled outcome, in which case it would be OIF, drawn from the Bernoulli with probability Fi. Okay, so that's what a distinguisher tries to do. Given the instance and the modeled probability and an outcome, it tries to guess whether the outcome is drawn from real life or from the model. And we say that a predictor F is outcome indistinguishable with respect to a distinguisher collection A if no ordinary A in blue A can distinguish real life outcomes from those drawn according to F. Okay. So it's a natural notion of indistinguishability. And, you know, if we think of our algorithm F as trying to give us a model of how the world operates, we're saying that this class of distinguishers shouldn't be able to determine that this is, you know, shouldn't be able to invalidate or falsify the model. Okay. Now, notice that I didn't say anything about the computational complexity of the members of A or how large the members of A are and so on. The definition makes sense independent of that. Okay. Once you have this notion, you can define a hierarchy of outcome indistinguishability, and the levels of the hierarchy will vary according to the degree of access that the distinguisher has to the predictor F. So for example, in no access outcome indistinguishability, the distinguisher never even gets to see the prediction F. It just gets individuals and outcomes. Sample access is the version that we've been discussing so far, but you could imagine a distinguisher that, say, gets Oracle access to the predictor and can ask about the values of the predictions on elements of its choice. Or even more powerfully, a distinguisher might have access to the actual code for the prediction function F and try to use that to determine whether outcomes are from real life or according to the predictor. And we're going to be focusing on this level of the hierarchy. So for all levels of the hierarchy, outcome indistinguishable predictors can be constructed given only real life outcomes data. So here's real life, P star. We get samples drawn from real life. So we have individuals and the outcomes that they experience. And based on this, we can build a predictor, P tilde, which is outcome indistinguishable with respect to this class A. We have to know A when we're trying to build the predictor, but we can do that. And the complexity of this, it can be computationally complex, but the sample complexity is logarithmic in the size of A, the set A. And again, the algorithm that builds the model P tilde only gets real life samples. It never sees P star, it never sees the real life probabilities. It only gets to see real life outcomes. So this is buildable. Great. Now, outcome indistinguishability arose from the in the sort of relatively new field of the theory of algorithmic fairness. And outcome indistinguishability, which is outcome indistinguishability, has given rise to a big class of fascinating field of work. It's deeply related to multi-calibration, and which preceded it. And in fact, recently there was a workshop at the Simons Institute on the many wonderful directions in which multi-calibration and outcome indistinguishability have been pursued. So let's look now at the fairness issue. That somehow or other, in the course of the excitement about multi-calibration and outcome indistinguishability, there's been a sort of view of accuracy as fairness. So for example, the literature even calls PI star, the real world, nature. But, and you could say that the philosophy has been, this is nature, we're going to learn as much as we can about nature, and then when it comes to fairness, maybe we'll try to do some adjusting, right? Maybe, yeah, whatever. But calling the real world nature is problematic. So one's chance of success is contextual. Consider a woman working in an egalitarian news organization versus working in a misogynist news organization. Where will she have a better chance of success? It depends on the context. Even who we are is contextual. The air, the water, the housing, our parents' connections, our education, healthcare, supportive colleagues, they actually change our attributes. They change the description of who we are, and therefore the effect of a prediction on us, or the prediction that we would expect. So we want to challenge this. And the way I like to think about this, and this slide isn't really essential for the rest of the talk, but the way I think about it is this. You could imagine a utopia in which we have individuals X, and there's some utopian probability that X would succeed at some task or have a positive outcome. And in the utopian world, sort of everybody is supported and assisted in achieving their maximum potential. And then there's some hard transformation which is the effects of the real world. So racism, sexism, poverty, lack of reproductive health care, lack of gender affirming care, failure to be exposed to ideas in banned books, and privilege, all of these things transform the ideal world to the real world. And this is some unknown and unknowable transformation T that maps utopia to real life. And T is very likely to be uninvertible. It probably destroys information. It bins people in various ways and eliminates distinctions between them. So, so this is my view of the world. And what I would love to be able to do is reverse T, but it's probably not reversible. And so the question is, can we think about maybe not getting to utopia, but moving in a better direction? So this is something that Omer Reingold, Guy Rothblum, and I are calling corrective transformations. And it boils down to trying to envision a better world and to see what this better world will look like. So in order to explain this, I need to introduce a little more formally the notion of a predictor and then a transformed predictor. So if we have a universe U of individuals, then we can think of the predictor as just a vector of whose dimension is the cardinality of U, and it's indexed by members of the universe, X in U. And so it's a vector of numbers between 0 and 1 of size cardinality of U. That's our predictor. And we want to introduce a transformed predictor. So we have a transformation tau. Tau is going to operate on pairs, individual X and the probability P of X from the original predictor. And it gives us tau of P applied to X. So we have this transformed vector now, or this vector of transformed probabilities. So that's what we mean by a transformed predictor. And we're going to define, so again, tau P of X is given by applying tau to X and P of X. And in particular, if P is equal to P star, the so-called real world probability, then we get this transformed predictor tau of P star of X. And it's mathematically well defined, even though we can't get our hands on the P star of X given a particular X. Because we can't know these probabilities, we don't even know whether they have to be integer or not. We don't know whether the real world is deterministic or in fact has randomness. So here's an example of a corrective transformation. Let's say we have a subgroup G, and in the transformed world, the scores for the members of G are boosted. Say add 0.2 to the scores of members of G. So what this says formally is that tau P of X is the minimum of 1 and P of X plus 0.2 if X is in G, and it's P of X untransformed for X is not in G. So that's perfectly well defined. Now, a corrective transformation could also be parameterized. And in this case, it would be paired with a learner that learns the values of some parameters by studying real life outcomes data, so training data. So we have input form XI and OI star, and we feed these to the learner, and the learner outputs some parameters pi. And so an example of using learned parameters could be that, say, if you're aiming for demographic parity, where you have two groups, A and B, and you want to ensure that the probability of a positive outcome should be the same for members of A and B. So one way to do this is to learn the base rates, A of probability of a positive outcome in A and PB of positive outcome for members of B. We set pi accordingly, and then we define tau P of X to be P of X if X is in A, and this convex combination of pi, so pi and 1 minus pi P of X for X in B. And that will give demographic parity. Now, where does tau come from? For the purposes of this talk, tau is just exogenous. we could think of this as kind of what we can hope that can be figured out by experts and wisdom and who employ people who employ ethics and policy and history and so on and so forth to come up with this proposed transformation. And for our purposes, we're just going to assume that it has been determined or decided that Q star, which I'm defining to be tau of Q star, would be a better world. So we have a corrective transformation, which gives us the world of Q star. And we have no data from this world because it's a made-up world. We're imagining something that's better. We want to know, what does this world look like? We have no data from this world. So the question that we're asking is, can we or when can we build a predictor Q tilde that is outcome indistinguishable from Q star, given that we only have access to real life samples? So remember, we started with utopia. We had some horrible transformation T. It gives us the real world. And we want to take a step in the direction of utopia, we hope. But in any case, we decided we're going to take this, we want to investigate tau. Tau of P star gives us Q star. We have real life samples from P star. We know we can use those real life samples to get a P tilde that's indistinguishable from P star. But we want to find a Q tilde that's indistinguishable from Q star. We'd love to get our hands on Q star. That's probably not possible. Can we get our hands on something that is indistinguishable from Q star? And the problem that we have sort of mechanistically is that we have no samples from this better world, this world of Q star. We only have real life samples. So is it doable? When is it doable? In order to answer this question, we need the notion of what we call a random instantiation of a predictor. So remember that we have a predictor. A predictor is this cardinality of the universe vector of possibly non-integers between 0 and 1 of scores. And a real life instantiation is obtained by, for each of the elements in the predictor, choosing P prime of X according to the Bernoulli distribution with parameter P of X, and that gives us P prime of X over here. So we're randomly instantiating, doing random draws for each of these Bernoullis, and we get a vector of Booleans. And that's a random instantiation of the predictor. And of course, if the predictions on the left are non-integer, there will be multiple possible random instantiations of the predictor. On the other hand, if P itself is Boolean, then every random instantiation is equal to P. Okay. So the key property turns out to be robustness of the transformation to random instantiations. The question that we're asking is, does tau of P look like the expectation from over a random instantiation of P of tau of P prime? Pictorially, on the left, we have, here's P of X, which has some value V. And if we look at random instantiations of the predictor P, then here's the value that we get. U1 is under the first random instantiation, U2 is under the second random instantiation, and so on. And by definition, the expectation over these random instantiations of P of X will give us the value P of X, will give us V. That's just by definition. And so now we look at this transformation. Over here, we're looking at V prime, which is the value of the transformed P on X. And then we look at, for each of these random instantiations, we look at the value that we get under that random instantiation for X. And we are asking whether these primed values that we get are also, whether in expectation, they are equal to V prime. So, yeah, okay. So that's the key property. So robustness actually gives us a complete characterization. Informally, we have a transformation which involves learning of parameters pi and the transformation tau. And if this thing is robust to random instantiations, then there is an algorithm for learning a Q tilde, which is indistinguishable from Q star. So this better world for any set A of sample access and no access distinguishers. On the other hand, if it's not robust to random instantiation, then even at the bottom level of the hierarchy, there's a very simple distinguisher that distinguishes any learned Q tilde from tau of P star. So we have this. I need. How many minutes do I have left?
You have approximately 5 minutes.
Okay, great. So our first example turns out not to be robust to random instantiation. And that's actually visible pretty simply. So if P is a half, then when we add 0.2 for members of G, we would have 0.7. And sorry, we would have 0.7. So that's what we would want the values to average to in the transformations of the random instantiations, but they won't. And the reason that they won't is because while we can add 0.2 to 0, no problem, we can't really add 0.2 to 1. We get capped. And so the values on the right are going to average to 0.6 and not to 0.7. And we will fail on the random instantiation. On the other hand, the second example I gave is robust random instantiations. Okay. So in my last couple minutes, I want to say a little bit about Joe and my appreciation for Joe. So I'm not sure exactly when we first met, but Joe was in the summer of I spent a few weeks at IBM San Jose, as it was called then, in the summer of 1984. And Joe was really in the thick of the early stages of reasoning about knowledge. And he was tremendously excited about it. And he introduced me to Yoram Moses, and Yoram and I worked on some of these things together. And I just remember that it was a tremendously happy visit, in part because of that. And in fact, working at IBM San Jose was my idea of a dream job. And I mean, it really was my dream job. And this was true even before I knew about Joe. And I applied for this job in 1983, and I didn't get it. But then I spent those 6 weeks, and it was a very productive 6 weeks. And, you know, I've been saying that what we accomplish depends a lot on our environment. And in that sense, Joe had a big impact on me. And in 1985, I applied again after my postdoc, and I got that dream job. And I think it was maybe 2 or 3 years after I was there, or even longer, before I would stop waking up and saying, I can't believe I got the job. And I'm deeply grateful to Joe for helping to create that environment and that world for me. In later years, before he left, but I was still there, but a little bit later, I'm also grateful to Joe for uh, helping me to say no. So this was actually literally helping me to say no. So something would come in and someone would ask me to do something and I wouldn't want to do it. And I would go to Joe's office and he would say, okay, now go, no, no, no. Now go, oh. So anyway, thank you, Joe, and thank you, audience. I'm really thrilled to have been part of the celebration of the 70th birthday.
Thank you. For Cynthia?
Yeah.
Yes.
Hi, Cynthia.
Moshe.
Hi, Cynthia. Can you hear me?
I can hear you. Be sure to speak up.
So when you start by saying the defining form of AI today is defining risk, I thought you're going to say extinction risk. Because this is now the talk du jour is AI posing extinction risk. So how can we apply your ideas to predict the risk of extinction? This is a one-time event.
I don't really have much training data, do I?
No, not much.
Oh, gotcha. Gotcha.
So, Joe, Moshe, is your question at all serious? Like, is there?
Actually, I've
Are
been
you
called by
asking
reporters.
anything?
I've been called by reporters asking me to give them the probability of extinction.
Right, yeah. What, I don't know what you say to them, but
I do not give probability.
you need to say, seriously, you need to say the notion is essentially meaningless.
Yeah.
And I mean, it's important to educate people that the notion is meaningless.
I like that answer. I'll use it next time.
Okay.
Depends on the time frame.
Any other question for Cynthia? Then Cynthia, thank you again.
Thank you.